Hi everyone, today we're going to be working with antiderivatives of functions. So we're going to be using what we know about derivatives to be able to ultimately work backwards and find antiderivatives of functions. So before we get into it, we're going to do some quick review here. So for number 1, it says to find the derivative of the following function. Now this is just a nice polynomial and I can use my power rule to find the derivative. So f prime of x is just going to be 2x plus 3 because I know the derivative of that constant 8 is just going to be 0. So for number 2, this function you'll notice is pretty much the same. It's really similar, just kind of varies by that constant. So my derivative is still going to be power rule. It's going to be 2x plus 3, and then the constant negative 100, its derivative is 0. So what you'll notice here is that the derivatives are the same even though the original function differs by a constant. And so I'm going to write that note here because that's going to be a really important idea when it comes to finding antiderivatives. So again, the idea is that the derivative is the same even though f of x, the original, differs by a constant. So because those derivatives go to 0, the derivatives end up the same. Alright, so for number 3, now we've got a trig function here, our sine function. So our derivative of sine is cosine. So we have cosine of x, and again the derivative 8 is just 0. For number 4, our derivative is going to be cosine of x, and again the derivative of that constant is 0. So even though we see again two functions that differ by a constant here, their derivatives are exactly the same. Alright, so our big idea then is being able to understand what an antiderivative is and how we find one. So an antiderivative is just a term we use to describe the reverse process of taking a derivative. So we used to go from the original function to a derivative. Antiderivatives are going to help us go from the derivative to the original, so going backwards. So let's take a look at this. If f of x equals x cubed plus 8, then f prime of x is going to be 3x squared. Now, it's saying if f prime of x equals 3x squared, then the antiderivative f of x, well, I know to get from the function to the derivative, it was from x cubed to 3x squared. So if I'm going backwards, the antiderivative of 3x squared gets me to x cubed. And we'll talk more about how that process works. Now, there's something else we need to account for, and that's the constant that we see in our original. Our derivative doesn't tell us any information about that constant that was there, but we know there was one. So the way we account for that is in our antiderivative we're going to put a plus c. To account for the fact that there could be a constant there, we're just not sure of the value. So let's talk a little more about that plus c. So it says if you look at the review examples, you'll notice that the constant term always disappears. Whoops. In the derivative. So again, just like up here, the 8 disappeared, here the negative 10 disappeared because those derivatives are 0. Right? This is because the derivative of a constant is always 0. So this means we can't determine the value of that constant just by looking at the derivative, so we write plus c as a placeholder for the unknown constant value. And you'll see we're going to do that over and over again using that plus c. So let's go to the next page and actually figure out and get down on paper some of these antiderivatives. Now I will tell you, You really need to know your derivative rules well to be successful here. If you don't know the derivative of a function, it's going to be really hard to find its antiderivative. All right, so for constant functions, if the derivative is equal to a constant, so for example, like f prime of x equals 3, then the antiderivative, f of x, would just be k, that constant, times x. So for example, if f prime of x, my derivative is 8, then the antiderivative is f of x equals 8x, and we're going to put plus c as that placeholder for the constant. Now the nice thing is we can always check if we have the right antiderivative, and we can check by finding the derivative of the antiderivative. So if I think f of x is the antiderivative, I'm just going to differentiate this. The derivative of 8x is 8. Since plus c is a constant, its derivative is 0, and that tells me that I matched here. So I know that this in purple is the correct antiderivative. Now let's say we have a polynomial function. So f prime of x equals a times x to the n. Here's how we're going to find that antiderivative. So it's going to be f of x. Now, when we're finding the derivative, we always subtract 1 from the exponent. So in this case, it's going to be the opposite. We're actually going to add 1. So I'm going to say x to the n plus 1. So we're kind of doing we are doing the opposite of what we do when we differentiate. Instead of subtracting 1, we're adding 1. Now, normally when we differentiate, we multiply that exponent times the coefficient. When we're anti-differentiating, we're going to divide. So we have a over n plus 1 times x to the n plus 1 plus c. So it looks like that's a little unclear. I just want to be sure we've all got that's a over n plus 1 times x to the n plus 1 plus c. So let's do an example now. F prime of x equals 4x squared. So for my antiderivative f of x, I'm going to add 1 to my exponent. So I've got 3. And then I'm going to take my coefficient of 4 and divide it by 3. So 4 thirds x cubed, and then again we have the plus c. So let's go ahead and check that. I can find f prime of x. Well, when I multiply by 3, that's going to cancel that 3, and I get 4x. Subtracting 1 gives me 4x squared, and that c, the derivative is 0, so you can see I match with my original, so the purple here is the correct antiderivative. All right, now one place we have to be careful is when we have a power of -1, right? We know that 1 over x is the same as x to the -1. Here we have to be really careful. Hopefully we recognize 1 over x is actually the derivative of natural log of x. So my antiderivative here is f of x equals the natural log. Now we're going to have absolute value of x plus c. So in my example here, if f prime of x equals 3 over x, the first thing I want us to recognize is this is the same as 3 times 1 over x. So my antiderivative now, f of x, is going to be 3 times the antiderivative of 1 over x, which is the natural log of the absolute value of x plus c. All right, now a lot of what's coming up next, again, is just going to rely on memorization and having really good, a really good memory of these derivative rules. So f prime of x, if f prime of x equals sine of x, then our antiderivative, here we have to be careful. F of x is actually going to be the opposite of cosine of x plus c. And that's because, right, if I take the derivative of negative cosine, well, the derivative of cosine is negative sine, so that negative times the negative will get me back to a positive sign. So the antiderivative of sine x is negative cosine of x plus c. Derivative of cosine of x is just sine of x plus c. And derivative of, if my derivative is secant squared x, the antiderivative is tangent of x plus c. And again, that's because the derivative of tangent x is secant squared of x. All right, secant x, tangent x, hopefully we recognize that as the derivative of secant x. Let's see, if my derivative is cosecant x cotangent x, that tells me my original function or my antiderivative is the opposite of cosecant of x plus c. Let me scooch this over so you can see that. And if my derivative is cosecant squared of x, my antiderivative equals the opposite of cotangent of x plus c. All right, exponential and logarithmic functions. Here's an easy one. If my derivative is e to the x, my original function is e to the x plus c. If I have 1 over x, we talked about this, my antiderivative is the natural log of the absolute value of x plus c. Let's see, f prime of x equals 3 to the x. So here, let's see, my antiderivative is actually going to be 3 to the x over natural log of 3 plus c. And this is probably one of the trickier ones. So let's think about that. Let's actually check this one. And I'm going to put it up here. Let's say my function is 3 to the x over natural log of 3. Now I'm going to rewrite that as 1 over the natural log of 3 times 3 to the x. So now, or plus c, I should keep that too. Now my derivative, 1 over the natural log of 3 is just a constant. So I'm going to keep that. Times the derivative of 3 to the x is 3 to the x times the natural log of 3. So now I can see these cancel, and I just get 3 to the x. And plus c, the derivative goes to 0. So I can see it checks out. So the idea is here, since I know the derivative of 3 to the x should have a natural log in it, since it didn't appear here, my antiderivative, it had to be divided. So that's a tricky kind of one to get your head around, so we can talk about that in class if we need to. From the last one, hopefully we recognize this. This actually comes from our original function of log base 3 of x plus c. The derivative would be 1 over x times the natural log of 3. All right, last bit we've got here is our inverse trig functions. This one, hopefully we recognize, is inverse sine of x plus c. This is our inverse tangent of x plus c. And we've got our inverse secant of x plus c. Sorry for the crowding in there. Now, these are all, you'll see the same derivatives, just opposite signs. So here, this is going to be our inverse cosine of x plus c. This is our inverse cotangent of x plus c. And here is our inverse cosecant, of x plus c. Inverse cosecant of x plus c. So obviously there are a lot of rules to have memorized. I would highly recommend flashcards or some kind of tool, because the quicker you are at being able to recognize these derivatives, the easier it's going to be for you to find the antiderivative. So the last thing we'll do here is a problem. We're going to find the antiderivative of this function, which means really we're just going to find the antiderivative of each of these terms. So let's see what that could be. Well, this e to the x is a nice one. That antiderivative is just going to be 3e to the x. For here, we're going to kind of use the reverse of that power rule. So I'm going to have x, adding 1 to 1/2 gives me 3 halves. I had a 5 here. Now, normally I would divide by the 3/2, but instead what I'm going to do is multiply by the reciprocal. Instead of dividing by 3/2, I'm going to multiply by 2/3. And there was a minus in between there. Let's see, I know the antiderivative of secant squared x is tangent x, so I've got plus 1/2 tangent x. And then this minus 1 over 1 plus x squared, I see that here. I know that's plus the inverse cotangent of x. So I'm going to simplify this a little bit. It looks like I have 3e to the x minus 10/3 x to the 3/2 plus 1/2 tangent of x plus cotangent inverse of x, and one thing I am missing is plus c. So that's what I think the derivative is. Now remember, we can always check by finding the derivative, and that should match if we did it right. So let's go piece by piece here, term by term. Derivative of 3e to the x is just 3e to the x. Here, let's see, I'm going to do negative 10/3 times 3/2. It's going to give me a negative 5 times x. If I subtract 1 from 3/2, I get to the 1/2. Derivative of tangent x is secant squared, so I've got 1/2 secant squared of x. And the derivative of my inverse cotangent is a minus 1 over 1 plus x squared. Plus c represents a constant, so that derivative is 0. So now if I compare, my derivatives match, and I know I found that antiderivative correctly. Alright, so that's all we need to really go over in the video. Really what's left is to do a lot of practice with finding these antiderivatives, because really what we need is for this process to be pretty automatic. Alright, that's it for today. I will see you back in class.